Hello, welcome to this webinar on the formalization of safety reasoning organized by Clearsy. It's part of a series of events designed to showcase how formal methods are used in practice today for safety critical applications. Today, I'm with Erwan Motin, Business Unit Manager in charge of development and validation of safety software.
Hello Thierry, hello everyone.
And with Julia Molinero Perez, Technical Leader, expert in safety software and system proof.
Hello Thierry, hello guys.
Both Erwan and Julia are going to present their method for formalizing safety reasoning, and to make things clearer, a technical example is used as an illustration. Some words about the target audience. This webinar is aimed at railways operators, signaling system suppliers, and certification bodies. Except the railway culture, this webinar does not require any prior knowledge or skill to be followed. The slides of the presentation can be downloaded in the handout section on the right of your screen. The video of the presentation will be available as usual on Clearsy's YouTube channel in the coming days. During the webinar, you can ask questions in the chat room on the right of your screen again, and we will answer your question at the end of the presentation. So let me switch to the presentation slides. Erwan and Julien, the floor is yours.
Thank you, Thierry. Okay. So more and more often, signaling systems are built by assembling multiple signaling subsystems. This is because operators want to buy these subsystems to different suppliers. For instance, they want to buy their onboard system to supplier number 1 and the zone controller to supplier number 2. Another case can be when you have an existing line with a legacy interlocking system and you want to buy a new CBTC. Now that you have bought your multiple suppliers subsystem, you want to know that every supplier will try to be compliant with their own tender. But who is going to guarantee that the whole system is safe? In other words, does a SIL4 subsystem plus a SIL4 subsystem equal to a SIL4 system? And how can we be sure about that? The first Clearsy reference is the work we carry out for New York City Transit. They have split the CBTC in 2 parts for a long time ago now, and they want to buy the onboard and the wayside systems to different suppliers. So they ask Clearsy to prove the safety of their tenders and to be sure that the whole system is safe. The same strategy have been chosen by the Paris Metro operator with the Optis project. It is deployed on line 3, line 5, lines 9, 6, and 11. And again, they ask us to verify the multi-supplier tender and to prove the safety of the whole system. This powerful technique is also used on the mainline projects. For instance, in Europe, the standards are written in order to have multiple onboard suppliers on the same line. So it's even more tricky since you have there the supplier number 1 for the wayside, called Radio Block Center in Europe, and you don't even know who will be the onboard suppliers. But you still have to have you still want to have a safe system. Here, for the revamping of the Marseille-Ventimiglia line between the France and Italy, the French operator, SNCF, has Clearsy to prove the tender. So by proving the tender, I mean prove the whole line. You can see that there are 2 different places where we can perform this safety activity. The first one is at the very top level it's the tender level. So we can help operators to correct their tenders and to be sure that their tenders are safe, even if the tenders are split in two, one for the supplier number one and the other for the onboard. And the other place can be at the design phase. So we can verify that the supplier's design is compliant with the operator specification. And this, we can do it even before the traditional development and validation phases. So you save a lot of time. Now I will give the end to Julien. He will explain you how this works and give you also a concrete example.
So thank you, Erwan. So we use the proof to formalize the safety reasoning. So what is a proof? A proof is a mathematical demonstration. It allows to deduce conclusion based on an explicit set of hypotheses, and these hypotheses are combined using only mathematical rules. So in our case, the conclusion will be the safety goal. For example, we want to show that collisions are impossible. And the hypothesis will be the set of requirements. These requirements are those that will be allocated to the different subsystems and so to the different suppliers. So that's the goal of the proof. We use the requirements, we combined it using mathematical rules, and we want to demonstrate that some safety properties are correct, satisfied. Here is an overview of the fundamentals. The first always consists in expressing the safety expectation. For example, we can say that no collision is possible, no derailment. That's the kind of safety goal we want to demonstrate. And then we will summarize the subsystem to their guaranteed properties. And that becomes the hypothesis of our proof. For example, if we are studying a system integrating an interlocking, then we may have something like interlocking never opens an entry signal of two incompatible routes at the same time. That's the kind of property of hypothesis we take on the interlocking. And then the key is to formulate the safety reasoning like a demonstration, like a mathematical demonstration, that is only based on the subsystem properties we identified before. For example, we could say, if we want to demonstrate that a train cannot derail, you can see here with the color green, that's the goal we want to prove, and then we can explain why. It is because the train moves only on routes that are locked by the interlocking, and we assume that the switch cannot move on such a route. So here we can see that we need two hypotheses to make this part of the reasoning, and then this hypothesis becomes some requirements for the interlocking. For example, we will have to verify that the switch can not move on such a route. The demonstration is always built using system and subsystems requirements. This can be requirements from tender, if we are talking about a new system or a new subsystem, or either from design documentation if we are talking of already existing system. At the end, proving the safety reasoning provides the assurance that there is no safety issue in the system, in its requirements, in any possible case without any simulation and based only on logic and mathematics. So one of the main advantages is that it can be done at the very beginning of the project. It is not necessary to wait the end to simulate the system. You can find issues at the very beginning. So if something is missing in the requirements, then you can be sure that the proof will never succeed. That's the key. So enough talk. Let's see on a concrete example how it looks like. The example chosen is one that can be applied in both a metro or a mainline context. So we will study a signaling system based on information exchanged by the train and some equipment on the track side. So that's the case for CBTC or for the new mainline standard in Europe, which is ETCS. So the principle is always the same. Each train is allowed to run only in its dedicated area. This area is computed by wayside equipment. So if we are in a CBTC context, I talk about the zone controller. If we are on a mainline context, I talk about the radio block center. So this wayside equipment will compute the movement authority and transmit it to the train. And one point that is key, one key point of the demonstration, of the safety demonstration, is that this movement authority shall always remain on the routes that are set and locked. And the routes are set and locked by the interlocking, not by the wayside equipment itself. I mean, not by the zone controller, nor the radio block center. So there is something here that shall be studied at the interface between two equipments, and we will see that. And the last argument is that, of course, we need that the train respects its movement authority. I mean, that becomes a requirement exported to the train. And with these two very simple principles, we can continue the demonstration one step before. So as I said, we can see here in the scheme that there are two concepts. There is the blue space, which represents the movement authority computed by the radio block center. If we take a mainline example, it is the same if we take a zone controller on a CBTC. That's the blue part. And there is also the green part, which is computed by the interlocking, which represent the routes that are set and locked. And if we remind what I said on the slide before, we just said that the safety depends on the fact that the movement authority are always computed inside routes that are set and locked by the interlocking. So here this means that at any time we want the blue space included into the green space. So that's the key of the demonstration. If we succeed to show that whatever happens in the systems, the blue remains always inside the green space, then we know that the train are moving only on routes set and locked, and so the train cannot derail on any switch. So this shall be established for any system evolution and also at the initialization of the system. In this case, the initialization is very trivial because there is no EMA computed at the very beginning. So the blue space is empty and the train cannot move. So there is no issue. But then if we can study when the blue space is extended, if an EMA is computed and extends the previous one, we have to show that it never goes downstream the green space limit. And also when the green space limit is reduced, to be sure that there is no more movement authority in this reduced space. So when a route is destroyed or cancelled by the interlocking, it must be proved that the EMA of the train, the movement authority of the train, which is the blue space, was reduced before. Of course, it is necessary because otherwise there will be a situation where the train can move on a route that is not locked. So here is the mechanism of the route destruction. Let's say that the interlocking wants to destroy the route and the space that was represented in green is now represented in gray. If we want to demonstrate the safety here, we need to specifically analyze the route destruction mechanism. How route can be destroyed by the interlocking, after which verification, how to be sure that the movement authority was reduced before? The answer shall be found in both subsystem requirements. What I try to say is that if you want to study the safety of this function, you need to study the requirements of the interlocking and the requirements of the radio block center. But in a multi-supplier system, who will do that? Of course, it is necessary it is the operators that shall do that. And here in Clearsy, we help on this point. So how does it work? Legacy interlocking system is that when you want to destroy a route, you turn off the signal at the entry of the route. So you show red aspects, and then you wait during an amount of time, a temporization, to be sure that the driver has seen the red aspect, and the train is now no more moving. So when the driver sees a red aspect, it starts emergency braking, and the train has to stop. And maybe 60 seconds later or 80 seconds later, the train will be stopped. And at this time, the interlocking see using the track circuit if the train is stopped before the route or on the route. And depending on that, the route can be destroyed or not. That's the historical safety reasoning of such route destruction. But if we study new technology system without any visual aspect signal on the track side, then you can see that this reasoning is completely obsolete. It doesn't work anymore because when the interlocking decides to turn off the signal, there is no more signal, so the driver will not see any change on the track. So you may say, okay, but the radio block center will see this change. Yes, and they will try to shortcut the movement authority. But what happens if this shortcut doesn't reach the train because of issues or in data transmission, because of network failure? So my purpose is to say, updating a new system with new technologies requires to update the safety reasoning. Of course, it implies changing in the historical system requirements, for instance, in the interlocking. In our case, if there is no more visual aspect for the signal, the interlocking cannot continue to destroy routes as it was doing before. So how does it work? You may have some kind of requirements like the route destruction. This requirement is allocated to the interlocking. It could say the route destruction shall be allowed only if the interlocking input, I call RGA to say route destruction authorized, is set to true. And this input is computed by the radio block center. And we expect to find a requirement on the radio block center that said, okay, the RGA output for a given signal shall be set to true only if there is no movement authority crossing the signal. And here we can see that it seems to work, because if there is a route destruction, it has been authorized before by the radio block center, and the radio block center authorizes it only if there is no movement authority crossing the signal, which means that there is no train crossing the signal. So the safety reason looks like that. In natural language, we can write something like the interlocking can destroy route only if authorized by the radio block center. So that's an hypothesis of our demonstration. It is written using the orange color, and it becomes a requirement allocated to the subsystem interlocking. Also, we know that we suppose that the radio block center authorizes it only if there is no MR crossing the signal. That's another hypothesis of the demonstration that will be verified later on the requirement of the radio block center. If we also assume that every train respects its movement authority, that is a necessary condition, of course, because if train doesn't respect movement authority, all of that will not ensure safety at all. So that's a safety expectation allocated to the onboard signaling equipment. Using these three aspects, we can deduce that there is no train threatening to cross the signal when the interlocking authorizes the destruction. And that's the demonstration, that's the point where we wanted to reach. You may notice that this demonstration doesn't depend at all on any scenarios or any simulation. It's just logic and demonstration based on hypothesis. So once we have such kind of demonstration expressed in natural language, we will try to give this demonstration to a mathematical tool, which is Atelier B, which is the qualified tool ensuring correctness and completeness of a mathematical reasoning. And the objective of these phases is to ensure that the previous reasoning was correct and complete. So the Atelier B doesn't know anything about the context. It only knows fundamentals, mathematical rules. So if we can convince these tools that using this hypothesis, I can deduce this safety goal, then I can be sure that nothing is missing. The set of hypotheses is complete, and there is no logical error in the demonstration. So now, if we look back to the process, what we did is that we took the requirements at the very beginning. So it may come from tender if you are an operator, or it may come from your design documentation if you are suppliers. And based on these requirements, we formulated the safety reasoning in natural language. These phases sometimes shows issues that must be corrected. So requirements must be either corrected, suppressed, or added. And once we think we have something that is correct, we go to the Atelier B, which is on the right part of the slide, of the scheme. And this Atelier B will give us the mathematical insurance. So sometimes it finds defects. The requirements will also be updated. Or other times it finds some minor adjustments, something like implicit hypotheses that were forgotten in the natural language reasoning. But once every hypothesis has been explicited and the Atelier B there is no more proof obligation to perform, you can be sure that the safety reasoning has been correctly formalized and the proof is correct. The next step will be to track the hypothesis and see if your suppliers have correctly implemented it. That's the key of the methods. So what are the output of this methodology? First, the list of requirement safety issue. This is the more important output. Here you can see directly if something is missing or something is incorrect. You can correct it before having trouble on your metro line. And the second point is the formal proof report. It contains the complete catalog of safety hypotheses used to build the demonstration. Each hypothesis is justified with its rationale. Without this hypothesis, the following scenario is unsafe, and we give you the sequence of events that should lead to a collision or derailment. The second point in this formal proof report is the safety reasoning report, which is a significant technical piece in a safety case. It simplifies commissioning, revenue service decision. This can be shown to the safety expert and to the authorities. And finally, the proven mathematical B models that will ensure with 100% the fact that the natural language reasoning is correct and nothing is missing. So just to focus on one of the outputs, which is really important, is the catalog of the safety hypotheses. Here you will find a lot of requirements that can be exported to the various suppliers. You may also find some safety rules to be verified on the data, and then you can use data validation, formal data validation techniques to be sure that these requirements are correct. You may also find some exported constraint to operation and to maintenance, just to be sure that the system is used correctly from a safety point of view. What is important to remind is that the safety proof provides a technical answer to this very simple question: why the system is safe? The characteristics of this answer are important. We expect mathematical rigor, system properties, irrefutable demonstration, non-ambiguous logic, design hypothesis, and that's the opposite. We do not want any answer based only on standard compliance, system documentation, proven in use, expert knowledge, scenario testing, trust, or even faith, I don't know. That's really the key of the methodology. And once you understand exactly why your system is safe, you can see the benefits coming, because there is a huge difference between just knowing that the system is safe and forget why, versus understanding exactly why the system is safe. In terms of safety, you are no more afraid about the safety issue in revenue service. This is no longer a matter of trust. Anyone who wants to understand can go into the demonstration and understand the demonstration and repeat the demonstration and be convinced. The explanation is logic, understandable, it is proved, it is mechanical in the arguments. And if you are an operator, you have a clear limit of the responsibility that comes with this kind of demonstration, because each subsystem is summarized to its safety properties. So you know what is under the responsibility of the supplier 1 versus the supplier 2. In terms of cost and planning, you saw that this kind of approach doesn't need any simulation, so we can do that at the very beginning of the V cycle, which allow to secure the planning and the cost reductions that comes with. And the last point, which is also very important, is about the availability and the maintainability of the system. Once you know exactly the reason for your system safety, you are now able to optimize the availability, the performance, and you are no more afraid by undesired side effects. So the safety questions are no longer restricted to a group of experts. You can share it with the new engineers in your company and so on. So the maintainability and the availability are also increased using this kind of techniques. So we are now at the end of this presentation. If you want to go further, do not hesitate to contact us for more information. We can show you the concrete benefits on your own project. We can perform proof of concept if you want. And also, Erwan and I will be in a business trip in North America at the beginning of January 24. So do not hesitate to contact us if you want to meet.